Next speaker up is Silvia Kusminskiy. We're looking forward.
Thank you. Now it's on. Very good. Thank you very much. And so I will be changing a little bit gears, and I will be talking or going back to antiferromagnets and basically exploring possible ways of probing and controlling magnons in antiferromagnetic materials. And in particular, so the first part of the talk will be on concentrating on 2D materials, and then I will be talking about mostly bulk antiferromagnets if there is time. So I already showed this slide and the tutorial last week, but since there are new people, so this is the current configuration of my group. So we are located in Aachen, in the Technical University of Aachen in Germany, and we do theory of hybrid quantum systems, with a quite variety of approaches, from more phenomenological approaches to also more microscopic approaches. So, and kind of the underlying thread theme of what we do is always to work with systems that have some magnetic degree of freedom, and as most of us here, we're interested in exploring ways of using magnons as information carriers, potentially taking them to the quantum regime to find some application in which they are useful, say, for quantum information processing. And this is also as an experimental result that I showed in the tutorial last week. So this, to my knowledge, is the first demonstration of a true quantum state of a magnon, which is a superposition of different Fock states, or well, a Fock state in the vacuum, or a Fock state with one magnon in it, in a setup in which there is a microwave cavity and a superconducting qubit. However, today I will be talking about antiferromagnetic magnons, and I think, okay, so one always talks about antiferromagnets in the sense, okay, there could be potentially advantages because there are no stray fields, they are robust to external fields. Of course, these make them also more difficult to control, but I think in terms of the magnon excitations, what is also interesting is that they inherit the rich physics of the antiferromagnet, and they can serve to, for example, for probing the underlying antiferromagnetic states and phases, etc. And also they have this fast dynamics in the terahertz regime, which could be useful for certain applications. So, but as I said, so I think it's important to find some kind of application in which magnons would have a certain advantage over other carriers. And if we think in terms of magnons in antiferromagnets, they are, if you want, quite special excitations. So we can look at, so we can look at, first of all, at the vacuum of an antiferromagnet, and one can see that it's actually a squeezed vacuum, so it presents squeezed vacuum fluctuations. And if now one goes with an optical drive, and it starts to excite magnons in a setup in which one basically has Raman scattering processes which involve two magnons and two photons, one will start creating or generating entangled magnon pairs, which also have let's say peculiar characteristics. So this is something which is a particular or unique in some sense about antiferromagnets. The other maybe motivation is one can think in terms of 2D systems and in terms of the magnon bands and topological properties of the magnonic bands. And so as we will see later in this non-collinear antiferromagnets, there is the prediction, or that so theoretically one finds that they can host these so magnon bands with non-trivial topology. The question is how to probe this, and I will be dealing with this in the next slides. Just because we mentioned this briefly yesterday, I will not be talking about this regime, but there are experimental developments, and we've also seen examples last week of actually coupling resonantly, coherently antiferromagnetic magnons to cavities in the microwave regime. If one considers magnon excitation, so magnons with frequencies, with low frequencies, let's say. Or also, as I mentioned yesterday, so now there are recent works that actually work with terahertz cavities and really coupling to these high frequency magnons coherently. So just I think this is quite an interesting development of the recent couple of years. So, but in this talk, I will be concentrating on coupling magnetic excitations of antiferromagnets to optical photons, and I will consider 2 different types of setup, if you want. So, in the first one, I will just consider the interaction of light with magnons, say, for example, as you could have in some kind of pump probe experiment, or just driving the system with a classical light field. And in the last part, if there is time, I will discuss what happens if one includes the back action of an optical cavity, which would allow to control the excitations via dynamical back action. So the outline is first, so I will be talking about probing and controlling magnons in antiferromagnets using optical photons. The first 2 are using circular polarized photons, either for control of magnon currents in antiferromagnets, or using circular dichroism as a probe of chirality, and therefore, I will try to convince you that this can be also a viable probe of magnon topology into the non-collinear antiferromagnets. And as I said, so the last part will be adding a cavity and looking at how we can enhance interactions and control the excitations via back action. But the first thing that we need to get clear, so to say, is how to model the light-matter interaction for antiferromagnets. And for this, I will take a phenomenological route based on an sort of scattering Hamiltonian, in which we have electric field modes, or so an incident field and scattered field, and the interaction is modeled by some optical susceptibility, which is spin dependent. And this one can work out, or one can write this susceptibility as an expansion in terms of different orders of the spin operators at the lattice. And what appears here, so these tensors here, the first thing that one can do is to analyze what are the allowed scattering processes, or what will be allowed terms in these tensors or matrices here, which are dictated by symmetry. Now, so this is a very general approach, and then we will be quantizing these spin operators to write them in terms of the magnon operators, and this will lead to the interaction between magnons and photons. But okay, so this is what I said. So these allowed terms can be derived from the lattice symmetry, but I just want you to, so this is something that we all know what these terms are, right? So this first term here is actually the one that gives rise to Faraday rotation, and one can write the permittivity as acquiring an antisymmetric imaginary part, which is due to the breaking of time reversal symmetry in the system because of the magnetization, and this gives rise to basically a photon which is scattering from one magnon. This is the usual one magnon Brillouin or Raman scattering term. So this is also this kind of this permittivity is also the one that is responsible for the rotation of the plane of polarization of light when it goes through a magnetized material. So the same term gives rise to these two phenomena, if you want. One is static, so when I have static magnetization, in the other one is looking at the excitation, so it's in some sense dynamic. So the other term that we have here is this next order. So if you think in terms of magnetization, and this gives rise to a Cotton-Mouton effect, and actually if we term, so this will be the static effect, and if we think in terms of scattering, this gives us a scattering of a photon, which will be scattered by two magnons. And the last term is oh, okay. So, so maybe what's common with these terms first, before we go to the last, is that if you look at the index here, they are single-side terms. They are actually microscopically one can obtain them by a perturbative calculation in the dipolar interaction. So the dipole interaction so the coupling of the electric field to the dipole, and in order to depend on the spin, it requires some spin orbit interaction. So now the other term is actually what is denominated in the literature also as a Flory-Loudon-Riemann scattering term, is a term which involves again scattering of a photon coming, creating two magnons or annihilating two magnons and coming out, and is dominant in antiferromagnets. And this is actually a term which is different. So, so the microscopic origin is different to the other two, and it's actually due to exchange, and that's also why it is dominant in antiferromagnets, because so the exchange interaction is a large energy scale. So now, how do we proceed? So this was kind of intuitive way of looking at these terms, but now we want to actually write this in terms of a Hamiltonian that actually give us the scattering between the photons and the magnons. And to do that, so the general recipe, if you want, is to write the electric field in terms of photon operators. So as usual, for the spin operators, we will use also the usual Holstein-Primakov transformation and cut to first order in the magnons, and then we will get some Hamiltonian, which is not yet diagonal in the magnon operator. So for that, we perform a Bogoliubov diagonalization procedure, which will express our photon magnon scattering term in the basis of the actual magnon modes of the Hamiltonian, of the given spin Hamiltonian, and by this I mean when we calculate the magnon bands of the mode of the model. So this is just to to put a simple example, which we will use also later. So if we have a given Hamiltonian, in this case, some Hamiltonian with exchange, some anisotropy in the z direction, and some Jelesinski-Mariya, we have a collinear antiferromagnet in the z direction. And if we calculate the magnon bands, we will get, without the MI, 2 degenerate bands, which is this black curve here, and with the MI, this degeneracy between the two bands is broken, and we have it here in blue and red. And this is what I call, so this alpha and beta are the two magnon bands in the antiferromagnets. And then when I talk about creating and annihilating magnons, I talk about this creating and annihilating magnons belonging to these two different bands, so alpha and beta. So I will call them alpha and beta magnons, and this just means that I'm creating them in the or annihilating in these bands. So if we put all these together, so we follow this recipe, what I will obtain is an interaction, which is this Flory-Loudon scattering vertex, in which we have now, in this language that I just explained to you. So we have a photon, which is scattering due to the magnons. The two magnon branches are indicated by these magnon operators alpha and beta. So this phi is a vector, if you want, which contains the two modes. And the vertex here, as you see, it's related, so it's dominated by the exchange in the model. And we have some scattering amplitude, which is also given by the frequency, volume, etc. So this is the usual normalization of coming from the normalization of the optical modes. So, and the whole the details of the model, the underlying spin Hamiltonian will be in these coefficients T and R. So, but this is a very general procedure, if you want. So given a spin Hamiltonian, you can calculate the vertex in this way. So maybe just diagrammatically, what this vertex is doing is just really creating and annihilating magnon pairs with opposite k due to conservation of momentum. So one can assume that the photon has basically zero momentum, and in this way you need to create or annihilate magnon pairs with opposite k. And that will be important in what comes next, because that means that with these magnons you will be able to probe all the Brulin zone and not just k equal to 0. Yeah? So then I will use this for first looking at if one can create or can use them to create magnon currents, and then, as I said later, we will use them to probe the topology of the magnon bands. So the setup that we imagine is as follows. There is some antiferromagnet, 2D antiferromagnet, in which there is some incoming light with some angle of incidence. And the question is, can one induce magnon currents with this light? And the mechanism that we are going to look at is this dominant mechanism in the antiferromagnets for the interaction with light, which is this creation of magnon pairs. Yeah.
One question, Silvia. So I think you have optical photons in mind, but is your approach generalizable for photons which are non-resonant?
So if you have non-resonant photons, you have also to worry about, Yes, but so then you will have a resonant cup, so you will create also single magnons, right? So what I showed you before, so the slide that I showed you at the beginning, for example, so the one with the strong coupling in a cavity, this is a one magnon, one photon process. Here you could have, if you think in terms of resonant processes, the dominant would be either one magnon, one photon. If it is, so it will be the absorption process that is dominant. You see, this is a scattering process, and if you're in resonance, you will have the absorption. And then what you can have is, if you are at the 2 magnon frequencies, is that you absorb a photon and you create 2 magnons. So you need to be resonance with the 2. So to have these processes of the 2 magnons, you have to be in resonance. Okay. So you have to have the frequency of the 2 magnons and not the single magnon that I showed you before. So here the scattering, the energy conservation comes as the usual scattering process, right? The photon, the outcoming photon, the energy difference has to match the energy of the 2 magnons. That will come in the next slide. Yeah.
In addition to this diagram that you have here, you also have the alpha dagger alpha, so scattering of alpha magnons, right? Does this one do anything?
Yes. So we'll. I'll come to this. So, but yeah. So this is a kind of schematic, and this is also to show that in this kind of processes, you also need to conserve angular momentum. So you conserve energy and angular momentum. Okay, and this is what I was just saying, that so in the Raman cross section, when you calculate, so these structure factors will enter, and the conservation of energy is the creation, so the difference in the energy of the incident minus the outcoming minus the incident photon has to be the energy of your magnon pair. Yeah. So. Yes. Good. So I don't have. So I'll go back to your question later. So in this case, the relevant processes are the ones that I'm showing here. Yeah. Good. And now, so since we know that we have to conserve angular momentum, so we need to think in terms of scattering of the light that imparts some angular momentum. That can either give or take some angular momentum of the excitation. So this is an example of this Raman cross section for normal incidence of the light in the 2D plane, and in this case we are looking at circularly polarized incident light, and we are looking at the scattering, the 2 scattering channels, so the light going out either circularly polarized or either right circularly polarized or left circularly polarized. And you see there is a big asymmetry between the 2 channels, so most of the scattering goes to the left channel when you come when you are incoming in with right circularly polarized light. So this is a particular example for this kind of Hamiltonian. So, and this shows that this form factor here at normal incidence, it is mostly concentrated at the K points of the Brouillin zone. Now, so we want to look at the photo-induced magnon current, and the first thing, so we can calculate it, but we can first think in terms of the terms that are allowed by, again, symmetry allowed terms. So what one can do is an expansion in the Raman interaction, and so since the Raman interaction is quadratic in the electric fields, so we will have so even terms here in terms of the incident and scattered fields, and that means that the optical susceptibility here will contribute only to odd orders so to odd orders in the expansion. And if one think in terms of the symmetry, so one sees that the third order, so that the one with 3 indices here, that would be with just 2 electric fields, actually vanishes, and that leads us to the first non-zero contribution, which is what we have here. And if one continues looking at the symmetry, so we're looking at this honeycomb lattice, so if one continues with the symmetry allowed terms, actually there will be only 3 independent terms of this object here, and one can see that only one of them gives actually a net angular momentum transfer. So we are left with 1 term, and if we express this field, so the polarization of the fields in terms of the angles that I showed before, so the symmetry allowed magnon current that we are left with is this expression, which is in terms of the value of this only allowed component of the optical susceptibility. It will have the sign of the inherited by the laser chirality, so right or left, and has some angular dependence, which is due to the angle determined by the incident light. So you see, then one can look at what is the angular dependence of the generated current. Here I'm doing it for the y component of the current. You can also do it for the x component. And what one sees is, well, okay, so this we see this already from here. So it will have opposite signs for opposite incoming circular polarizations. And we see that for completely perpendicular incidence, the generated current is 0, and this is because of symmetry, so that the 2 contributions will be completely symmetric and the total current will be 0. And if you are in plane, then you don't have basically the projection of this, so you need some circular polarization in the plane, and if you are coming in plane, then the light is effectively linearly polarized in the plane, and you also do not generate any current. So this kind of
I just want to grasp on something very, very simple, if possible. So initially, you have incident light that has circular polarization along some axis, and angular momentum of the universe should be conserved. So what happens is the light reflects back up, and then the chirality flips, but the total angular momentum is the same. Is that right?
So you have to impart the 2 units of angular momentum to create the magnon pair. Now, there is an issue with how you define the chirality. So yes, I'm not sure if this is what you're asking.
I was sort of thinking about the picture you showed just before this, where you showed the right and left circular polarization changing. So that would be 2 units of angular momentum if it's pointing in the same direction.
Yes.
But
And then if you measure
H bar
it,
and minus H bar, so I was thinking maybe it's pointing in the opposite direction.
No, if you measure it, I guess it depends if it's misleading.
Is it transmission or reflection?
Yeah, so I think so. As I showed it, it should be transmission, right?
Okay.
So it's not.
Okay.
Yes.
So you are producing 2 units of angular momentum in your sample somehow.
Yes.
Okay.
Yes.
Good.
Yes.
Thank you.
And then so it depends if you will look in reflection or in transmission,
Okay.
what you see. But
Okay,
yes,
thank you. Thank
so
you.
this is thanks. Okay, so this tells you that in principle there is the possibility of have these magnon currents by these 2 magnon Raman scattering. Now, The question is how large is this effect? So for that, actually, we did the calculation for a particular model for MNPS3. I'm very bad, so this is manganese. I'm very bad with names, compound names. So MNP3. So with the accepted parameters of the literature, and we calculated the current not just with this simple symmetry considerations, but actually we did the calculation with Kubo. So looking at the current operator, doing Kubo to second order, you obtain an expression for the current, and then you can look at what are the contributions. So this will be a matrix. You will have some diagonal components, and you will have also an off-diagonal components. The diagonal components are dominant, and also then you will have Stokes and anti-Stokes components, so creating or annihilating magnons, and the dominant contribution on low temperatures is this diagonal Stokes component. And we looked at so if you translate this to with inverse spin Hall effect to a voltage, how strong the voltage that would be, and it is for an incident current that looks large, but it's apparently reasonable. It gives you, in principle, numbers that should be measurable. Yeah. So so this is also a dependence on the temperature, which takes into account some phenomenological decay of the magnons with the temperature. So in summary, so we expect that, or we propose that one could use this circular polarized light to actually generate magnon currents, which you can actually control with the polarization. So which direction you can actually control with the polarization of the light. Yes.
I'm lacking some steps behind. So if you're plotting the inverse spin Hall effect voltage, then there's more to the game than just your creation of two magnons, but don't you need then some directivity that I have missed to pump or kind of have a magnon accumulation in your device so that you can measure it via spin Hall effect? So I'm not getting together your Raman scattering picture.
What
this magnon transport to the detector?
Yes, so you control the direction with the light, and you detect it in a certain geometry, which you have to determine once, or I guess you have to do it consistently, right?
But don't you need to accumulate then either magnons or deplete magnons at this detector?
Wouldn't that be what the magnon currents are doing?
Indeed, but what so the piece that I'm missing is when I'm going from this abstract scattering picture that you have presented to this device picture. So how I need to translate in my head the directions or the propagation directions of the magnons in this device if you have an incident light.
So, well, okay, so here I showed you the white component of J, yes? So the same you can do for the X component, and that would give you, and then given a certain angle, you will have a current in a certain direction in the XY plane.
Ah, okay, then
Is this?
I missed this connection basically. Thank you.
So here I just show, yes.
A slightly different comment or question, but
Yeah.
can you go to the next slide?
Yeah.
So you said is that the optical intensity is 10 to the 12 watts per square centimeter?
Yes.
That seems a little high to me.
Yes. So I had the same worry, I actually asked Alexei Kimmel, and if I remember correctly, he said it's okay.
Is it a pulsed excitation or is it CW? What is the assumptions?
There is no assumption. So it's just the protocol we do not. So the time-dependent protocol in which you do this, we do not.
Because if I have yeah, that's a lot. That's really a lot. I mean, I'm gonna vaporize everything. Yeah, that's
okay.
Just, I mean, so maybe go ask him again. But by the way,
I think it's fine if it's only about if it's a problem if you absorb it.
Because
oh, I see. So you're saying the statement is the material doesn't absorb it at all.
No. It's just no.
It passes through.
Well, it's scattering, but there is going to be some absorption, I guess, right?
Yeah.
But then how much? But for what I understood in this kind of pump probe experiments, they can reach to this kind of intensity.
Peak, like if you have an ultra short pulse, and then you're talking about the peak of the ultra short pulse, then I agree. But it only lasts for femtoseconds.
Yeah, and and
that's like few cycle pulse kind of.
Okay, and if that is and the question is if that is enough to detect then to.
Right.
To detect.
On the other hand, the voltage that you're giving is like millivolt scale, and as experimentalists, we can measure much smaller voltages than that. So that millivolt is like my handheld meter.
So I think the idea is what. So these are the numbers, but so the numbers that we kind of took from the literature, but this looking at this kind of pump probe experiment, which is the available things that we had at the time, right?
Yeah, if it makes you more comfortable, like the noise floor of a good lock-in is like maybe 5 nanovolts per root hertz, something like that.
Okay. I see. Thanks. But I was also worried about this number. But then, so as I said, the question, it's a very valid question, right? If you have this pump, and we did not look at this, right? If you have this, so if you do actually kind of pump, in this case it will be pump, but then you will be probing with the leads, right? If this is actually if the time scales are.
So there is a way to measure even down to nanovolt voltages and these kinds of pump electrical measurements. So that's actually one thing that my group does really, really well.
Okay.
And we can talk about it if you care about the experimental details, which I think you don't. But it's actually really nice because
no, I do.
You can take advantage of essentially the bandwidth, so you can amplify the pulses with very, very low 1/f noise.
Okay.
And become very, very sensitive in those kinds of situations. So
but then that would be much. So that would make this kind of proposal much more realizable.
But if you look at the numbers, I mean, I just did a back of the envelope calculation. So the power is fine if you go to the femtosecond regime, but on the other hand, if you go to the femtosecond regime, then the average voltage that you get will not even be nanovolts; it will be picovolts or less.
Why?
Because you cannot measure
this is the problem. Okay, this is the problem of the time. Okay.
You can only measure a certain average over time. No, not femtosecond. I mean, you can make Boxer averaging.
So with time domain heterodyning, and you can generate pulses of, say, 50 picoseconds at the rep rate of the laser. Yeah. So then you can measure easily down to tens of nanovolts at those timescales.
Yeah, but
so don't divide by the laser duty cycle.
Not by 10 to the 12, but it's single nanovolt maybe, but probably less.
Okay, we can work the numbers out later. It doesn't matter. Okay, thanks.
No, but that So if there is a way, so I'm actually interested if there is some kind of way of making this work, of course. Good. So then next, so when maybe kind of some historical so the history of the development of this. So when we were looking at this and actually at the scattered light. So what we realized is that there is some connection with the very curvature of the magnon bands. So it kind of popped out in the calculation. And we realized that, so I think this system is a collinear antiferromagnet, so the Berry curvature is 0. So basically what we got here is that if we would look at the dichroism, so the circular dichroism, so the scattering, the difference in scattering between left and circularly polarized light, we would get the expression for the Berry curvature in this case, but this was a very fancy 0 equals 0 case, because for this topologically trivial case, the Berry curvature or the Chern number would be 0, and the circular dichroism also. Yes.
Do you have a way of getting the Chern number out? Because you're you're integrating the Berry curvature over something that's weighted by your occupation numbers, though.
Yes, so I will show this now. Yeah, exactly. So I said Berry curvature. So the Berry curvature would appear there, and then we realized that integrating. So if we would integrate it, and so this will give us this dichroism signal. The same mathematical expression, but it was 0 equal to 0 because we are in a topologically trivial case.
But also you'd get a non-universal result in general, depending on the occupation numbers, right? Because you're not weighting different parts of the Brillouin zone with different factors.
Let's go to so I will show the expressions. Maybe that solves your question. So, well, let's see. Okay, so this leads us to consider a system which has topological magnon bands, and so that the Chern number of the bands is not 0, and to look if what we found in the topological trivial case extends in some way to the topologically non-trivial case. So this is this goes in the direction of probing the magnon topology using optics. So maybe just a very simple slide to say why would one be interested in this, and the issue, maybe the main issue is that in fermionic systems one can just put the Fermi energy, with the Fermi energy we can put it at wherever we want, for example in the gap, and look at so occupy the edge states and just probe them. In this case we do not have, so in the case of magnons we do not have this possibility, so one has to look at how to occupy these states and how to measure them, right? The other, and this is a little bit of a technicality, if you want, which is if we, with these antiferromagnetic magnons, if we look at how the procedure in which we use to diagonalize and obtain the magnon bands. So we end up diagonalizing a non-Hermitian system, so that this enters. So the one has to be a little bit careful on how to calculate these topological quantities in this case, and how to connect them with observables. Yeah. So. But okay, the general idea is that we would, so if we have a non-trivial topology, there will be chiral edge states of the magnons, so edge currents of the magnons, and this can give us maybe a hint that if we have a chirality probe, it might be a good way of probing the topology of the system. So this is our tool, so the circular diachroism, and we are not going to actually be probing the actual edge states. We are going to look into the possibility of probing really the bulk. So forget about the edge states. We are going to probe the bulk, so the Chern number. And this goes back to what I
quick question.
Yes.
So this kind of topological stuff is something that I work on a little bit, and there the issue usually is how to probe something topological in bulk, and it's very hard. As far as I know, in the fermionic system, it's difficult. Dennis and I have a paper submitted, the one he showed yesterday, that using Shubnikov-de-Haas oscillations, you can see this Mexican hat type of band structure that is kind of a feature of a topological system. And you have the two bands crossing as they invert, and then you have these splittings, and so that's kind of a bulk signature that you just measure. We obtain it in say transport. So here, why can't you? You said you cannot really probe the. I'm still confused a little bit about how you define your topological. The formula is the same, right? But of course, here you don't have Fermi energy.
So so it's a little bit different. So you just need to take into account that when you diagonalize the Hamiltonian in the magnon excitations, you end up so you diagonalize something that is non-Hermitian, and that's why then you have to be careful when you define, for example, the Berry curvature in terms of right states, eigenstates, etc. So this is just a technicality. I think it's not. So in any case, in our case, everything is real. It's not an issue. But I'm just saying that it's a little bit different than when you do it in fermionic systems. That's just a technicality. The other issue is how to measure, right? And that you have two options, in my opinion. Either you really try to look at the edge states and be sensitive with something to these edge states, or you look at some non-equivocal, so some signature of the topology in the bulk. So what I know that there have been in these 2D materials, which I did not put in the slides, but it's, for example, neutron scattering experiments in which they show that there is a gap in the bands. So and they say, okay, this is a topological gap, but so there is a gap. Yeah, exactly. So there is indirect evidence. So they say, okay, the Hamiltonian that models the system is a Hamiltonian that has the MI and basically the MI and it is expected that is topological, and then they fit the magnon bands that they obtain with their spin model to the neutron scattering results, and they fit well, and they fit the gap, but still is kind of indirect evidence. Right?
The topological and the trivial cases, the band structure is very different, but the spectrum, because for some of the topological system in electronic system, when you have the bands inverted and not, depending on the system, they look exactly really the same.
Yeah, not really. So then So that's why. That's why. So I think it's an open issue how to demonstrate unequivocally that these are topological. So that the underlying spin system has magnon bands that present non-trivial topology, as far as I know. this has not been done yet. So good, and so this is what we try to address here, and so now this is what I told you before. So this is not what this is what I told you before. So if we have a collinear antiferromagnet, like the one I showed you in the example before, so this will be topologically trivial. Now, if you have a ferromagnet with finite DMI, this will have, or the model will predict that this have finite non-trivial topology. Now, the issue is that now if we want to probe optically, if we have a ferromagnet, this the dominant scattering term will be intermittent scattering terms that only probe k equal to 0, that only probe the gamma point. But it's usually, so it is in these systems that the Berry curvature, most of the Berry curvature is not at the center of the Brillouin zone. So actually, if you want to probe the Berry curvature of the bands, you need something that is able to probe or to see all the Ks. And this is what these kind of processes do, because so we generate in these magnon pairs, and you can probe all Ks. Yeah? And this is more or less the idea now, that if we have a canted antiferromagnet, then you will have a canted non-collinear antiferromagnet, so an antiferromagnet in the plane, and which cants out of plane. You will inherit a topology from the ferromagnetic state, but you can also expect that you will be able to use these processes to probe it. So that was more or less the idea. So this is what I just said. So now we look into a canted antiferromagnet out of plane. So for this case, so you see that the Berry curvature is concentrated at the K points. And if you look at the Chern number of, I think this is of the lower band. So if you vary the Dielosinski-Maria interaction and the magnetic field, so every time that you have a finite Dielosinski-Maria and a finite magnetic field, then you will be in a topological phase. And so what we now try to see is if this circular dichroism, so what I told you before, the difference in scattering between the left and circularly polarized light gives us some information on the Chern number. So in this case, and this goes to the question that you had before, actually for this kind of system, so the magnon processes are, so if you come with left or with right light, so you scatter it again into the opposite right and left, and actually you will scatter mostly either or create or annihilate mostly alpha phonons or magnons or beta, so lower band or upper band, depending on the polarization of the incoming light. So this is what is written here. So a scattering channel determines the magnon band that you are mostly seeing. And they come with opposite signs. So actually, when you actually take the difference, so you calculate the dichroism, you will have a finite signal.
Question.
Yeah.
This is all done in bulk.
Yes.
Or is
no. This is just a bulk.
Yeah. So there's no edge state in this.
No,
system.
no, exactly.
That's where all the C's are calculated, the Chern numbers are calculated
There's
as well.
the band. Yeah. Good. And okay. And so what we show? Okay. No, I don't have the equation here, but I can show it to you later. Is that actually, if you calculate this dichroism for these processes that I showed you here, actually it is a pretty accurate mapping of the topological phase diagram. So it's 0, and this is what we were finding this very fancy 0 equal to 0 that I was telling you before. So it is 0 for the topologically trivial case, and it gives you a non-zero signal, and it changes sign between the topological phases. So it's kind of a probe of the Chern number. Of course, it's not going to be quantized, right? But so it's either finite or not, and it changes sign. I do have an analytical expression later in the slides.
Can you actually show it's proportional to the Chern number?
This is the issue. And no. So it gives you the Chern number plus stuff that you hope it's small. Yes. But I have the expressions in a couple of slides later. Yes.
I probably misunderstood the formulas earlier, but so it looked like the situation would be that you send in a photon that has either right or left circular polarization, and then it flips from right to left or left to right.
Yes.
And then you would create magnons with some definite plus k minus k.
Yes.
At a specific k for each photon, is that right? Or no?
Well, so then you do it for so if you look at then controlling the frequency, you can basically probe all photons because you fix the energy.
Okay, you're going to get all of the energy conserving processes, and
yeah. So this is sorry,
average over the.
This I didn't say. Yes, sorry.
Okay,
this is integrated in frequency.
Okay. I understood that you were measuring the Berry curvature at one point in the Brillouin zone.
No. Sorry, this is integrated. Integrated in K and integrated in frequency. Now, this brings me to the next slide, that if you do frequency resolved, the frequency resolved circular dichroism, and if you know the density of states, you can actually obtain the distance between these two peaks in the signal will give you a measure of the topological gap. And this, you see, the density of states is mostly concentrated at the K points. So this is why also this gives you kind of a measure of the gap. And so this is frequency resolved in this case.
I'm still confused when you say the topological. So gap. So for the trivial and the non-trivial cases, so one case has a gap, the other one doesn't?
Yes.
So one is what, the method would be like gapless?
Yes.
The trivial,
yes. Well, yes. Yeah. Yes, I think so. This is correct.
So you actually have a picture of the band structure?
This is it. So for
the non-trivial and the trivial.
Wait. Let me see. So if you go down in field, so you see, I think you just have to start following these bands. Okay, I think the trivial one would be the one that I showed. It would be something, no. No, yeah, what I'm showing here, but for b equal to 0, for b equal to, here I don't have it, this is true, but for b equal to 0, there should be, it should be trivial. It's just, I don't remember if this closes here or not. I have to look for it. I think it should close the gap. But then, yeah, I have to look. I don't remember exactly how they look like. But you see it here, right? So maybe this is the gap, and as you go to 0, it closes. Yeah. So it's not. So I think you're thinking in terms of you go from like in electronic systems, in that you cross. So there is a phase transition where the gap closes
Then it
And-
reopens inverted.
Yeah, and I think here is just closed.
Well, there you also have semi-metals, vial type, system, and it's metallic. That you can have gap, and then it can close, and it's gapless. I'm just wondering whether the gap is a good
No, yeah, I understand.
quantity to say it's topological or not.
So what I don't know, I think if B is 0, then the gap will be 0. What I don't know if you have a finite B but 0 DMI. This I have to check. I don't remember how the
Because this would be very different than the electronic system, right? There you can measure the gap before and after the inversion, but it doesn't mean much.
Yeah, exactly.
Right? You don't really know. The band structure can look the same.
Yes. Okay, but I have to check. I don't remember. So good. Okay, but maybe just to conclude. So now I showed you a little bit. So if you want an idealized, or maybe let's put it this way. So one can start looking at the different processes in line to what you were asking, right? And so the different processes, so the different kind of excitations that you can say create with the incoming light, and then you see that actually you will have different types of processes. You can create 2 alpha magnons, you can create 1 alpha and 1 beta, and you can have these interband processes that we denominate. Okay, the labeling doesn't matter, but in principle, all of this can be present, and each of these processes either actually probe a different region of the Brillouin zone, and the total signal will be a sum of all this, right? And the question, which is like how to increase the process that you want and suppress the ones that will not give you information on the Chern number, right? And this maybe it's a little bit also to what you were asking. So if now if you compute analytically the very curvature, what you will see is that you have some part that you can express in terms of these different processes that are probed by the circular dichroism, and there is some other part which is also, it's only present if the system is topological, but this you cannot access these terms, or this would be they're there, but so you have an incomplete mapping, if you want, of the Chern number, well, the very curvature, and therefore the Chern number. So the hope is to make these terms large and in comparison to these terms. Yeah? And this is what we have been doing now. And what actually we realized is that this ferromagnetic contribution, which is actually is the one that so there will be also is a contribution from the processes that you also would have in a ferromagnet. This give a large contribution, but these are these interband terms at k, which in principle you could only have at k equal to 0 if your other states are not occupied. So to activate them on the whole Brillouin zone, you have to populate first the magnons at a finite k, and then use the light to make the vertical transition. So this is what we think, or that this is what we are in the process of writing up, that you could do this by a pump probe experiment, and that the density of states is high. So basically, you can come with a pump which uses these two magnon processes to populate magnons at the K point, and this is the most so the densities of states will be is maximum there, and then come with a probe and use this population to activate this process. And now, if you compare to what I showed you before, so this is what I showed you without populating these states. So this is this mapping that I showed you before between the circular dichroism and the Chern number. Now, if you activate these processes, you have the possibility of getting a larger signal. The issue, and we don't know very well why it is happening, is you also get these zeros in the diagonal. So you also get a zero of the signal when the system is actually topological. And we are trying to understand. So there is a competition here that leads to this line, but we do not. We haven't found any nice explanation except that there is some cancellation. Anyways, so this would, in any case, this would give you. We think it could be worth trying in terms of having an optical probe of the topology of the systems without probing the edge states. Maybe I will just very. To conclude, I will not have time to look into this, but so this was my promised negative alpha, but I have to skip it. Just to finish, so the other option would be to actually be able to probe the edge states. Yes, and this is also something that my student Ipshika is looking into in collaboration with Johannes Knolle, and the idea is to try by also kind of either by pump probe or also by a cavity enhanced interaction to reach to have an instability of the population of the edge states and not of the bulk, so that then you pump the system, you create magnons, but mostly at the edge, and that you can probe this then with pump probe, but just that to enhance the signal from the edges. So so this is actually for a ferromagnet on a honeycomb lattice, and okay. I don't have I had a plotting which shows that we find that it depends on, depending on so you need to do some fine tuning, but it's possible in principle to have this enhancement of the population of the edge states, but not of the bulk. So I hope that I convince you that optical probes are promising for both probing and controlling magnons in antiferromagnets. And I have here, so thank all the collaborators that participated in the works that I showed you. So Emil Viñas-Bostrom and Terje Parvini have been working, or were the main leading forces behind the most of the work that I've shown you, and so Yingxing has started now to work in the last part that I showed you in looking at different processes. Sanchar, he's here, and Vitor Vittencourt was a postdoc in my group. Well, I think I leave you with this, and thank you for your attention.
So further questions? And why do you give the microphone, man?
No, I need to play the chair. I'm not entirely, sure I actually understood how the chair number calculation goes, because I'm used to chair numbers for the electronic system. Like the standard one is like the BHC model. You just add, you calculate all the, even in the continuum model, you just consider 2 bands, the insulator, right? So you have 2 bands and you sum over all these states in the lower band. And then you have, sigma plus and sigma, C plus and C minus, and the difference is in, an integer. And of course there you have a gap, and you can put the Fermi level in the middle of the gap because it's an insulator. And then you can cut the system, make an edge, and find the edge states. It seems to me that they're very similar. But for instance, your your omega plus and omega minus, you have the 2 terms, and then you to calculate the chair number, you should integrate over the Brillouin zone. So the question is...
Yeah, so I showed just the very curvature. Then you have to integrate over the Brillouin
so when
zone.
you integrate, what is the contribution of the 2 terms? Do you have them, separate? Are they bigger, smaller? What is the dominant?
You mean here?
Yes, if you integrate those.
So integrating this, as you said, it will give you the chair number of the upper and lower band. And the issue is that these, for example, these terms are go linear with DMI. So the more topological they are, so this is why. So it's not a nice. We need to change the name, but we call them topological rest terms because they are these rest because they are these terms that we don't like, but they are still there and topological.
So that doesn't give you an integer.
No, the whole thing gives an integer. So this plus this.
Yes.
Yes, and that's the thing. So with the RCD, you are only able to probe this here. So the funny part is that, and this is what I was trying to explain at the beginning, is that if you are in the topologically trivial case, this goes away, and this part, so the analytical expression is then it's equal for the dichroism and for the chair number, but it's zero.
It integrates to
yes,
zero.
exactly.
Yeah. But in the topological regime, when you integrate it, there's no cancellation of this rest terms when you add them.
No, maybe there is some way of finding some combination of so we were thinking maybe if there is some combination of other, instead of just taking the circular dichroism, if you can cancel out, but we did not find any smart way of doing this. So we are left with them. So so Yingxing has been looking into seeing if he can cancel them by some combination of the processes, but he has not yet found the way.
Okay, I have a question. Thank you for a great talk, which I didn't follow all of it. So this is a kind of nitty-gritty question, but so let's say that I want to do this experiment. I started thinking about it, and I think I'm thinking about it wrongly. So I'm going to explain the analogy so that you can understand my thinking and the wrongness of it, and then I'll ask my question. So if I want to do a measurement of an edge state of an electronic system, so for instance, one thing that people have done is they have some topological insulator, and then they want to measure the edge current. They'll measure the magnetic field. They'll apply a current, and then they'll measure the magnetic field around the edge. And they'll see that they can do current reconstruction. And then, like my colleague Katya Nowak does this kind of thing, and then they say, "Oh, okay," but that's a local measurement, and the measurement itself is not actually sensitive to topology in any way. It's just measuring a current, and so it has to measure at the edge. That's the only way that you can conclude that you have an edge current. But what you're doing here is intrinsically sensitive to the topology.
Yes.
So I was thinking about this and I got kind of stuck because the edge state is localized to the edge, but somehow I think that in your calculations, you're actually calculating for the whole system at once.
Bulk. Yeah,
Yeah,
there are no edge states.
So actually, I just measure it anywhere, and this is going to reveal the topology.
Yeah.
Okay, thank you.
So maybe just as so I did not show it here, but so we were also trying to do is connect this kind of measurements with the quantum metric of the bands. And we have we have certain expressions there that could give a little bit of more an insight of why this is working. But so in that is more general if you want, but in this case, so that we found ourselves as a justifier, like kind of more general formalism if you want, but in this case it's just doing the calculation and just so analytically see. So okay, the previous, so the original manuscript was kind of a hint, and then numerically we saw this works, and now what my student Xing did is to actually calculate analytically and just identify all these terms, and you just see that it's there. Right?
I'm curious about how generic these formulas are. So you gave specific examples where you knew you had some topologically non-trivial bands in a honeycomb lattice, but these formulas look very generic, and the way you described them sounded very generic. Yes. Can you apply the same reasoning essentially to any model that you think has a non-trivial topological band for magnons?
So this goes to what I did not talk about it. So the way we kind of, so if you look at the PRL that I showed before, so there you basically what we introduce is or what we show is that you can do this through light matter coupling. So which comes from an expansion in the vector potential of the light. So now this is a little bit of an issue because here the magnons have no charge, but we are kind of doing this with a minimal substitution. So things work in certain cases.
Are you saying in which have gauge-dependent results if you use this P dot A versus length gauge?
So we used the minimal substitution, P plus E. Okay? It works if the system is charge neutral and if you can write the Hamiltonian as in the spin. So when you calculate the effective spin Hamiltonian, the K appears in this form. So in that case, this works. And so we are trying to write this up now. So that tells you that for any spin Hamiltonian that fulfills this, you can actually try to calculate. So calculating the light matter couplings. So, and we found a relation between these light matter couplings and the quantum and the different components of the quantum geometric tensor. Now,
so
and maybe
you're suggesting that there are some additional conditions that have to be fulfilled, but if they're fulfilled, then these terms exist for any.
Yes, and then the group of Johannes Knolle did this for Kitaev spin. So I think it's a spin. So something with which he did it for 2 examples. I'm not remembering now with the examples they are, but where you have spin-answers excitations, and they calculated both with this formalism, the more general formalism that I'm telling you, and doing the actual calculation, and they showed that they are equal, and they showed that they can get I think also the signal. Did they calculate that? Okay, and I think I think they also calculated the dichroism signal. That part I don't remember, but they used the same kind of formalism for a completely different system. This is what I'm trying to say.
Thank you.
Yes.
I just want to say that perhaps tomorrow we can continue the discussion.
Yes.
Yeah, because we have time, a lot tomorrow, and today I don't want to be rushing you guys to back to the hotel and then to the place we have to go. So maybe if we have some quick questions that we can probably wrap it up, and so we can call it a day.
Yes.
Scientific day. All right.
Thank you.
More questions? Then let's thank Silvia again.
And let's thank all the